serial bus using synchronous communication system where we need a clock pulse and one wire is there in the bus for passing the clock pulse, as because it's a synchronous communication. And the second one is that another wire is used to carry the data. And here is the examples which devices actually use the inter-IC bus. And inter-IC bus is implemented on a single motherboard or printed circuit board, and you know it's a very small or tiny area. So it has 3 modes. Depending on the modes, we have different data transfer speeds: classic, fast mode, and high speed mode. And these are the advantages. The main advantage of using inter-IC bus is that it reduces the board size or printed circuit board size, and the board, if the board size is reduced, obviously the cost is reduced, and obviously the connection complexity is less. All the devices or all the components in this inter-IC bus are categorized into 2 parts. One device will be acted as a master, and the other devices or other components will act as slave. So we have a slave address of 7-bit slave address, and always the data transfer direction are controlled by the master, and we don't have any fixed length of data transfer. Rather, after sending 1 byte of data, there will be one acknowledgement or negative acknowledgement to ensure the reliable data transfer. Of course, there is a possibility of multi-master capability, and it is also possible. So for that reason, we have to use some arbitration procedure so that one master can act as a master for the whole bus system. So here is the definitions of masters and what a masters can do and what a slave can do. We have seen the main task of master is that to provide the clock pulses, and it selects the slave address, and depending on that selection, the data transfer direction is maintained. The master may ask the slave to send the data, or the master may select one slave to which slave the master will send the data. So everything is controlled from master end, and the slave only responds to the timing information as well as to the direction that a master provides to a slave by selecting the slave address. So this is a typical structure of inter-IC bus, where you can see we have a serial data connection and one is serial clock connection, and through the serial clock connection, who provides the clock pulse? The microcontroller here is acting as a master. It can provide the clock pulse. But you can see that we have 2 microcontrollers. So here is the multi-master concept. In case of multi-master concept, either of microcontroller A or microcontroller B can act as the master, but they will have some arbitration procedure. Using that procedure, only one becomes the master for a certain period of time. As a whole, the inter-IC bus can be in a state of idle mode, or we can treat that the master node is in the transmission mode, or we can treat that the master node is in the reception mode. So if we consider in this way, we can identify the status of the bus. So if no one is transmitting, in that case you can consider that the bus is in the idle state. If the master selects one slave address that I like to send some data towards you, so in that case the master is in transmit mode, or the master can select one slave that I like to receive data from you. In that case, the master is in the receive mode. So every time we we do consider the master node states to define the status of the bus. So this is the electrical diagram where you can see that how the bus is uh, uh, the bus architecture is shown, where you can say this is a device 1, this is a device 2, and we have the SDA, SCL, we have two pull-up register, and inside the devices we have serial connection and serial clock connection, data connection, input connection, and output connection. And the logic of this bus is that it also follows the wired and technology or wired and logic. That means if any node sends any zero signal, a logic low signal, the whole bus will be in the dominant state. If any node sends the signal, in that case the status of the bus will be in the dominant state. That means either the master is sending or the master is receiving. So the whole bus bit transfer or data transfer is controlled depending on the status of the clock pulse. And in my last class, I have told you that the data transition, if any node is sending data, whether the master is sending or the slave is sending, doesn't matter. If in that data, if there is a transition from 1 to 0 or 0 to 1, so what is called transition? Let's see that I'm showing it in digital format. So let's say 0, 1, 1, 0, 0, 1. So we have some transitions where you can see that here we have a transition from 0 to 1. But we don't have any transition there. But here we have a transition from 1 to 0, and next no transition, but another transition. So you can see in the data we have three transitions, and these transitions these transitions are to be made when the clock pulse is in the low state. Only then the change of data is allowed. And when the clock pulse is in the high state, you can see this is the high state. So in that case, the data should be in the stable line, or data should be maintain a stable line. It means two things it has ensured. One is that any bit that should follow a 100% duty cycle, 100% duty cycle for a certain data bit in a certain clock pulse. You see, this is the clock pulse. Within this clock pulse, either 0 or 1 should be stable. And if there is any change, in that case, that transitions needs to be made for a certain when the clock pulse is in the low state. So this is the thumb rule. Next, this, as it is a synchronous communication, but we know that in synchronous communication we don't need any start or stop byte, but we are not using any start and stop byte. Rather, we are using some start condition and stop condition. So it's not a byte, rather it's a start condition and stop condition. So whenever the clock pulse is in the high state, the sender or the transmitter has to make a transition from 1 to 0. So for one clock pulse, it will maintain that, and the actual data will be transferred. If the data is 1, so one transition is made. If the data starts with a 0, if the data starts with a 0, let's say 0. So in that case, that 0 will be maintained. But the data for a fresh data start, the start condition defines with this block. This block. That means when the clock pulse is in the high state, the transmitter has to make a transition into the 0 state. Whatever state it is, but it should maintain a transition towards a 0 state. And the stop condition is reverse. Whatever condition is there, in the SDA line, the transmitter has to make a transition into one state or logic high state. You can see, and at that time, of course, the clock pulse is in the high state. Okay, I have talked about the 7-bit, or in case of extended version of inter-IC bus, there is a 10-bit address, and these amounts of 2 to the 7 amounts of components or peripherals, you can say, can be addressed by using this 7-bit address. And we have some special functions, some other special functions are for address extension starts with all 1 or starts with all 0. These are some special functions. Apart from these special functions, other unique addresses can be used for slave addresses. So how a first byte looks like? The first byte looks like this. This is the data format. We started from by providing one slave address. So the 7-bit slave address. Then the microprocessor informs whether it is doing any read operation or write operation. The master node actually informs depending on the 0 and 1. So you see the 0 means the slave written to by master. That means master is transmitting. And 1 means slave read by master. That means that master should receive the data from the slave. And this part is sent by the master up to this first byte. And afterwards, the slave sends one acknowledgement signal with a logic high signal. So the master can be a transmitter only, or the master can be a transmitter. Just after that, it will receive, as because master is controlling. And oppositely, when the master is transmitter only, in that case, slave will be receiver only. Or otherwise, when the master is first transmitting the address, at that time the slave is in the receiving mode, and after that the slave becomes a transmitter, and at that time the master is the receiver. So only these possible connections is there in inter-IC bus. Okay, I think on to last slide I've covered for in the last Friday. So it's the new part today, that after sending the data or any address, one acknowledgement should be sent. So first of all, acknowledgement is sent through the data line. We have the 2 lines. You can see that we have 2 lines. One is SCL that always maintains the clock pulse, and we have the data line, and 2 data lines are there. One data line for transmitter and one data line for receiver. Okay. Now you see the transmitter makes a transition. This is the start condition, and after that, at first the slave address will be started. After sending the slave address and blah blah blah, there will be an acknowledgement. And if the receiver receives the data successfully, whether it's a slave address or it's a data, because data can be transferred from the slave towards the master. So whether it's a slave address or data, doesn't matter. There will be one acknowledgement signal by providing a logic low signal for a whole clock pulse. For a single clock pulse, you see, for a single clock pulse, it will maintain a logic low signal into the data line. The receiver will send this logic low signal. So this will be treated as an acknowledgement from the receiver end. Because sender makes the transition for a start, sender makes the transitions for data transition from 0 to 1 or 1 to 0, and you see the transitions are made during the low signals, during the logic low signals for the clock pulse. But the sender will receive one acknowledgement signal just having a logic low signal from the receiver end for a single clock pulse. So you see that the master and slave receivers pull data line low for one clock pulse. Whether it's a master receiver or master is in the receiving mode or the slave is in the receiving mode, they pull data line for one clock pulse after reception of a byte. That means after each and every single byte, there will be there will be an acknowledgement signal. And the master receiver leaves data line high after receipt of the last byte requested. And the slave receiver leaves data line high on the byte following the last byte it can accept. So you see that to be into the low part, the master receiver will leave the deadline for high for one, will maintain the data line high, just receive of the last byte. That means after getting the one byte of data, whatever the condition is in the master receiver part, it will maintain a high signal to provide this acknowledgement signal as a low signal. Or if the slave is receiving, in that case, it will also maintain one the data line with a high signal after receiving the one byte and following the acknowledgement signal. So this is how the acknowledgement can be transferred. And finally, when the acknowledgement can, these are the scenarios when the acknowledgement signals can be sent. So first of all, acknowledgements can be sent from the slave. So let me draw one figure. So just one figure. This is our SDA. This is our ACL. This is our master. This is our slave 1, slave 2, and let's say slave n. So we have n numbers of slave and one single master. So let's say for time being, we consider the master is transmitting something to slave 2. So when the acknowledgement will be sent, so first of all, the master will select the slave address, and in reply to that, the slave will send one. So let's say this YOLO is acknowledgement. So it's a logic low signal. It's a logic low signal for one clock pulse. So after reception of the address received correctly, the slave sends the acknowledgement, and also after reception one data byte, the slave also sends the acknowledgement. This is one case. The second case is that from slave to master receiver. The first one is the slave to master transmitter. That means it is the transmitter, it is controlling everything, but the slave is only reacting or responding. But this will never happen, because slave to master receiver, no, because slave cannot initiate anything. Because master receiver can generate the acknowledgement upon this scenario. So this is that scenario, that master is asking one slave that you can send the data. In that case, the slave will send the data and the master receiver will send the acknowledgement towards the slave. So already we know that is a slave and a master. The master can be a transmitter only, and at that time the slave will be in the receiving mode, and the master can be in the sorry, and the master can be the transmitter only, plus after that it will be receiver, and the slave will be in the first receiving mode. At that time it will be in the, after that it will be in the transmitting mode. So these two are interrelated. These two are interrelated. And these two are interrelated. So this is that scenario. The master receiver to slave, one acknowledgement is sent after receiving the data byte from the slave. But the master transmits, the master selects that, okay, send me the data. The master actually sends the slave address to select that slave address, so that the slave can send the data. So these two scenario never happens. These two scenario never happens for the acknowledgement purpose, because we don't have any from slave to master receiver. No, this doesn't happen. And also the from master to master transmitter to slave, this also never happens. Okay, let's talk about the negative acknowledgement. As we have the acknowledgement, we have also the negative acknowledgement. And when we can, when the system can allow the negative acknowledgement, is that when there is any error in the data transmission or in the data transfer, is there any error? In that case, negative acknowledgement is sent. And you know that negative acknowledgement means I have not received the data correctly. Similar to earlier figure, the only difference is acknowledgement is sent with putting one logic low signal for a one clock pulse. The negative acknowledgement is logically the opposite thing. The receiver will maintain the logic high signal for one clock pulse. So you see, there is no transition. There is no transition. So that means the receiver will identify or receiver will transmit or maintain one logic high signal for a certain clock pulse. This clock pulse, after getting the 8th byte, you see that there's the, after getting the 8th byte, if the receiver has not correctly received the data, and it will maintain one clock pulse with a logic high signal. So that's the simple thing, and these are the possibilities, same possibilities, that negative acknowledgement will be sent from slave to master and from master receiver to slave. This two never happens. And when the negative acknowledgement is sent after the address not received correctly, after the data byte not received correctly, if the slave is not connected to the bus, and also if the last data byte not received correctly, in that case master receiver doesn't send an acknowledgement, negative acknowledgement. Okay, so this is all about our signaling mechanism. Do you have any question? You can ask me. Then afterwards, I will go to the data format. The signaling mechanisms is already been discussed. Now the simple thing is remaining in the data format. Okay, so as a whole, if I show you the signaling mechanism, here is our SDA line and here is our SCL line in the inter-IC bus. So again, I am drawing that same figure, SDA and SCL. And here is our master node, slave 1, slave 2, slave n. the slave addresses are defined through the defined through 7-bit, and the masters control everything. And you see the sends the sends the clock pulse. You see that the clock pulse is sent by the master. Just I'm drawing some clock pulse so that into the SCL or serial clock line. And who provides that? The master provides that. And the rest of the nodes are connected. This is the connection, and these are the nodes connected, and so that they can receive the same clock pulse. And you see that here into that at the very beginning the start condition, any data transfer, it starts with the start condition. And what is the start condition? We have seen that for a high clock pulse, the sender will starts with the data transition from 1 to 0, and after that this is the MSB. The data byte will be sent. That means the most significant bit of the one data byte is sent first, and after that, after sending the data, if the data is correct, 1 byte of reception, if the data is correctly received, in that case acknowledgement is sent from the slave or receiver, you can say. Because acknowledgement from the slave, because this we have treated as the slave address. At the very beginning, the master is providing the slave address. So this is the slave address, and after that the act from slave. And after that, the data can be sent in this period. The data can be sent either by the master or by the slave node. And after each and every data byte transmission, there will be an acknowledgement signal from the receiver or negative acknowledgement from the receiver. And afterwards, at the end, the stop condition is there. So multiple of data bytes can be transferred during this phase. So there is no fixed length of data transfer. And the stop condition, you have already know that when the clock pulse is in a high state, there is a transition from 0 to 1. So as a whole, the data format, data format, not from the sender to receiver or receiver to sender, but how we have distinguished differentiated the data format. This texture part can be treated from master to slave, and the non-field part you can consider the white part is the part from slave to master. So you see the start condition, S starts for this, and who provides this start condition? The master is providing the start condition. And the stop condition, P. The master is providing the stop condition, as because this texture part. Okay. Just a minute. স্যার আমি একটা ক্লাসের পরে কল দিচ্ছি স্যার। আমি স্যার একটা ক্লাসের পরে কল দিচ্ছি আপনাকে। ওকে ওকে আধা ঘন্টা স্যার। ওকে okay, sorry. Okay, so you see that start condition and stop condition are sent. This is a data format. This is not you can don't treat it as a signal. Rather, the flow of the data is shown in the data format. So from master to slave, or from slave to this is from slave to master is shown by these white blocks. So master sends the start condition. After that, just after that, master selects one slave by providing the slave address, and it selects the direction of the data. That means whether the master is going to write or read. So that is maintained by this bit, And if this part is received successfully by the slave, only then it will send an acknowledgement signal with a logic low signal. Acknowledgement with a logic low signal. So the likewise this act from the slave. And after that, depending on the data byte transfer direction, the data after one byte, one acknowledgement, another byte, another acknowledgement. These acknowledgement or negative acknowledgement is also possible. So bar, a bar is not acknowledgement or you can say negative acknowledgement. So this is as a whole the data format. So the data format is continuing where the master reading from slave. More specific, this is the master writing to slave. The master is writing to slave. That means master is the transmitter. You see W bar works with 0 and the master is reading from the slave. Master is reading from that means one pin, the one will be here. That means both the cases are mentioned or are demonstrated here. That means here the master is writing means master is the transmitter, slave is the receiver, and master is reading means the slave is the transmitter, master is the receiver. And you see that from master to slave and from slave to master. And you see here in this case the data is in the blank space, means the slave is transmitting the data. And this second acknowledgement, the first acknowledgement is sent by the slave, but the second acknowledgement or negative acknowledgement are sent by the master. So as a whole, this is the combined format. Combined format, start condition, stop condition. In the first case, the slave address is provided, read write signal, acknowledgement. In this case, the slave is transmitting, or the slave can send the acknowledgement, negative acknowledgement. As a whole, this is general format, and it repeats continuously for the whole communication system of inter-IC bus. So, so that's it about the data format. If you have any question, then you can ask me. Then I'll move to the multi-master concept. Multi-master concept means this scenario. Multi-master. There are two masters. Two cannot work simultaneously as a master. So we have to follow some arbitration procedure. So arbitration procedure similar to the wired AND technology. The multi-master situation requires two additional features of the inter-IC protocol. One is arbitration. So arbitration is the procedure by which competing masters decides final control of the bus. And you know how can we define the arbitration does not corrupt the data transmitted by the prevailing master. Rather, arbitration is performed bit by bit until it is uniquely resolved. That means using the identifier of the multi-masters or using the master's ID, the arbitration is done, and that is the similar to the way we have seen in the control area network bus. So that's it. So the multi-master, so only one node can be acted as a master. Okay, so how that master can be selected using the arbitration procedure that we have seen into the control area network bus. So this is a scenario that where we have data line, single data line, but we have a single data line, but data 1 and data 2 are two masters condition, and they have started their start condition doesn't matter, but afterwards in this phase depending on their identifier, one loses and one wins using the wired AND technology and the identifier values that using the dominant and recessive state condition, one wins and one loses. So that's it for the arbitration part. Now, how the error can be checked, because we are using the acknowledgement and negative acknowledgement. Inter-IC bus defines the basic protocol and timing. Protocol errors are typically flagged by the interface. Timing errors may be flagged also, or in some cases could be interpreted as a different bus event. How the error can be treated? Because if the receiver finds that the data should be uh, transition of the data should be maintained when the signal is in the clock signal is in the low state. But if any data transition is made when the clock signal is in the high state, so that's an error. So this is how we don't need any redundant bit, likewise the CRC or parity or the checksum. The receiver is also following the clock pulse. You see, the receiver can also see the clock pulse, and the data transition should be made when the clock pulse is in the low state. But if any, and when we say that one error has occurred, when we say that 1 becomes 0 or 0 become 1. So if any data transition occur not in the state when the clock pulse is in the low state, in that case the receiver will identify a one error has occurred. So this is how the acknowledgement or negative acknowledgement can be sent. And also there is a timing error may be flagged, or in some cases could be interpreted as a different bus. Glitches is another type of error. So it's it depends on the it is related with the clock information, and also incorrect data, or in case of the bus is locked. And we can say that error can be checked if we add some extra byte for making the checksum. Checksum means the whole data value can be added and can be sent as additional data. So checksum is also possible in this inter-IC bus system. The bus recovery. When the bus recovery is needed, when the master and slave get out of the synchronization, that means the clock pulse is not available to them, the same clock pulse is not available to them, or a stop is omitted or missed, stop bit is not there, or any device on the bus holds one of the lines low improperly, and the shorted bus line, that means some short circuit has occurred. In that case, these are the exceptions when the bus becomes locked. And in case of if the SCL can be driven or the clock pulse can be sent, the master may send extra clock until the SDA goes high and then send a stop condition. So this is an initial step the master can take. Or if the SCL is stuck, that means SCL is in the running phase but the SDA is in the high state. There is no predefined stop condition. So the master can take the role. And if the SCL is stuck, only the device driving it can correct the problem. So it's these are the exceptional areas the bus needs to be recovered. And this is the last part. 5 minutes left to finish the lecture. These are the available inter-IC bar devices. As at the very beginning of this lecture, I have told you that the small devices or small scale network or small scale embedded devices uses the inter-IC bus. Let's see which devices it uses. Analog to digital converters, we have seen these are the integrated circuits or the chips. We have seen weighted summing amplifier, we have seen successive approximation method, or we have seen the R12 ladder circuit. So those converters uses this inter-IC bus. Bus controller, the bus repeater, real-time clock, deep switches, and LCD LED display drivers. So these are the available devices where we use the voltage level transistor, multiplexer switch that is used for the telecom purpose. These all are small scale embedded devices. Those are using the inter-IC bus. So this is the theory. I'm just providing you the list. And finally, who are the users? The telecom operators, the data processing devices, the instrumentation devices, automotive devices, and consumer devices. Likewise, our TV, DVD, these are the consumer products. These all uses this sort of components, and this sort of components requires inter-IC bus. So benefits, already I've talked a lot about the benefits of inter-IC bus, because the main benefits is it reduces the printed circuit board size, the main board size, and thereupon obviously the cost is reduced, and the connection complexity is very simple, very less in inter-IC bus. So not I'm going point by point, but as a whole I'm telling you about the benefits. So that's it. We have some benefits from the designer's view, and we have some benefits from the manufacturer's view. So these are the theoretical part. I'm not going through, because I think you can already got the main uh, flavor of using inter-IC bus, and why do we need that, basically to reduce the cost and to make the printed circuit board more simplified way. So that's it from my side, and we have completed our major protocol. One is high scale embedded protocol, that is the control area network bus and protocol. And the second one is small scale embedded system protocol, that is the inter-IC bus, and it's related to protocol. So that's it. If you have any question, then you can ask me. Otherwise, I have some declaration for you that on inter-IC bus and on CAN bus, we'll have our second class test quiz. So when can we take that quiz? Akib and others. Next Friday? Is it possible?
স্যার একটু অ্যাকচুয়ালি দেখতে হবে স্যার।
Okay, fine.
মানে
So
আরেকটা অন্য কুইজ আছে তো স্যার, দিয়ে দিছেন।
so thing is that only one quiz I have taken, and up to 8th of January we have the semester. So I should take at least 2 more quiz, and thereupon I may give one assignment. But the second quiz will be on control area network bus and inter-IC bus. Okay, so my preferable time is on Friday or next Tuesday. So please let me know. Okay.
ওকে।
Okay. So thank you, and see you on the next Friday. Allah Hafiz.
আসসালামু আলাইকুম।